this presentation is all about transform of derivatives and solving some simple ODEs. Now, this is the driving factor with our motivation for studying these Laplace transforms. When I first introduced this topic, I said, okay, Laplace transforms are, in many cases, a much more efficient way of solving linear ODEs because they streamline the ideas and especially the initial conditions. So we're going to show you how that works today. All right, so just to refresh our memory, a Laplace transform, remember, is an integral transform where you take a function, say little f of t, you multiply through by this exponential and you form this improper integral, which is a function of s. Now in this context, usually lowercase letters represent, say, function of t, and uppercase letters, functions of s, represent the corresponding Laplace transform. Okay, well, these are the kinds of functions that we're looking at, so-called piecewise continuous functions and functions that satisfy some sort of exponential growth condition. This is something that we don't really pay too much attention to. We just assume that we have functions like this when we take transforms and Laplace transforms. All right, we've looked at the Heaviside step function that switches functions on and off, and we've spent a bit of time showing how to describe functions in terms of this Heaviside step function. Now here I've sort of defined the value to be half, or the average of the jump. Some textbooks do it differently. It doesn't change anything about the transform if you just sort of change the definition at one point. And we've been looking at this table and working with this table. Now, this table is particularly important when you want to take inverse transforms. Okay, we have a representation for calculating Laplace transforms, but no explicit form of the inverse. So this table is very important. I mean, there is an explicit form of the inverse transform, but you need complex function theory to handle that. So we just sort of ignore that. Okay, so this is the basic building block from which we're going to solve ordinary differential equations by using the Laplace transform method. Okay? Think of f here, little f, as a solution to some differential equation that we want to determine. Okay, let's talk about the transform of derivatives. Okay, well, it's claimed that if I take the Laplace transform of some derivative, then it's just this expression here. And in fact, if you look down your transform of tables, this is contained down here. Here it's got g prime. I've used f prime up here. So you can see here, you've actually got the identity. Okay, so why is it true? Well, essentially it's just integration by parts. Okay, so I'll just prove the first one, and then there's a general one for, say, the nth order derivative. So we use integration by parts. Okay, so we just use the first principles, our definition of the Laplace transform. But instead of having little f in here, we have f dash or f prime. What we can do is, say, integrate by parts. Let that be u and let that be v dash. So u dash, if you differentiate with respect to t, is going to be minus s e to the minus st, and v is just the integral of this, so it's just f of t. So just using the integration by parts formula, and noting that this is an improper integral, it's u times v minus the integral of the product that you just thought up, or you just constructed. Okay? So that's just integration by parts. Now, what's happening here? Well, it's pretty clear what happens when t equals 0 in this case. I'll get 1 times f of 0. But it's not so clear what happens as little t approaches infinity. Well, if we think back to our tacit assumption on f, this condition actually forces, as t goes to infinity, this to go to 0. Okay? So this sort of growth assumption guarantees that as t goes to infinity, this will go to 0. Okay? Now over here I can take this minus s out the front because I'm integrating with respect to t here. And lo and behold, this is just the Laplace transform of little f. So I'll get s times big F of s here, and I'll get f of 0, little f of 0 over there. Okay? So that's why it works. Now, so let's say you forget that. You just integrate by parts to come up with it. Now there is a more general sort of nth order derivative identity or expression. In your table, what do you have? Well, you have first derivative, second derivative, and third derivative in this one. Okay? But you should check with your table in the end session to see exactly what you get. From memory, you'll get at least the first and the second order derivatives. Okay? You'll get at least the first and the second order derivatives. And if you need to calculate anything higher than that, well, the pattern's pretty clear once you know the first and the second order derivative, the transform of those things. Okay, so how can we use this result? Well, we're going to use it in the solution of differential equations, but let's just see how we can use it, say, just on regular transforms. So suppose I have, say, a continuous function, little g. So the integral, the little f of t is defined, well defined in that way, using the integral. We're asked to show that the Laplace transform of this is just the transform of little g divided by s. Okay, so
Sorry, Chris, g is continuous?
Correct, little g. Okay. Yep. Okay. So how do we do it? Well, instead of taking the transform of this, let's actually differentiate it and take the transform. Okay, we know by the fundamental theorem of calculus, since, say, g is continuous, I can differentiate this, right? So by the FTC, the fundamental theorem of calculus, the fundamental theorem of calculus says that I can just differentiate here. These will cancel each other out, and I can replace tau with little t. All right, so let's take the transform here then. So just using this line, So take the transform over here, and then apply our transform of derivatives. This is just S big F of S minus little f of 0. So here I'm using transform of derivs. And what's little f of 0? 0, right, because if I go up to my definition, if I plug in little t equals 0, well, I'm integrating from 0 to 0, so I've got to get 0. Okay, so I end up with the expression big G of S equals S times big F of S, so rearranging that I get the following. Okay? Now, if you look in your table, the table that we've been using, it's right down the bottom. That one. Okay? Right down the bottom. But it's just a transform of derivatives. Now, you may be able to get it other ways, but it's kind of a neat way of using the derivatives. Any questions for that one? What's the significance of the problem? Well, to take the transform of this, all you really need to do is look at the function inside and take the transform of that, and then divide by S. Okay, so we now reach the ultimate aim of Laplace transforms, to solve initial value problems in a simple and straightforward way. In particular, we're going to look at solving ODEs where the right-hand side has discontinuities, jumps. Okay, so what method is this useful for? Well, linear ODEs with constant coefficients. Okay, in particular, say, you know, in class we've been looking at first order and second order problems. Well, the Laplace transform can be used for, say, third order, fourth order, as well as first and second order. Okay. Now, the idea is to take the original IVP, or initial value problem, what you do is you transform the problem into an algebraic setting. Then you solve that problem in the algebraic setting, and then you transform everything back to get your original solution. Okay? So what a transform does, it transforms the problem to another state, if you like. You solve that, and then you untransform everything to get back to the original state. Now, that may sound a little bit weird, but the method is best explained via examples. So that's what we're going to concentrate on. Okay. So here's a fourth order linear problem. This isn't too bad to solve using the characteristic equation methods, but there are four initial conditions to deal with. Most of them are 0, but I'm going to show you how we can use the Laplace transform to solve this problem. Okay? All right, now there are definite steps with these kinds of solution methods. So we should try to see, form a pattern with all the steps, and we'll talk about that in a minute. Okay, so let's talk about the ODE. The first step is to take the Laplace transform of both sides. Okay, so now you might want to sort of draw a line down here because there's a fair bit of writing to do here. So let's take our Laplace transform of both sides. Now the Laplace transform is a linear operator, so I can break up that left-hand side into two bits. Now here I've got a pretty simple right-hand side, just 0. The Laplace transform of 0 is 0. Okay, so okay, I would expect you to know that the Laplace transform of 0 is 0. Okay. Everything all right? Yep. Now, deal with these. Well, let's use transform of derivatives on this first one. Okay, so okay, so we're going to use this with big N equals 4. Sorry, little n. So we're going to use this with little n equals 4. Okay? Now, just to sort of clean up the algebra a little bit, I like to sort of make this I like to write it in terms of little s and a capital Y. Okay, now you see why that's important in a sec. Okay. All right, so using our transform of derivatives, we obtain the following. Well, what's the transform of derivatives here? Well, it's going to be something like the following, just using the formula or the expression on the previous page. Now this is just big Y of S. Okay, so you may look at that and go, hang on, Chris, you've actually made it more complicated now. Well, not really, because now what I can do is apply the initial conditions straight into this bottom line. Okay, well, let's have a look at the initial conditions. That's going to be 0. That's going to be 1. That's going to be 0. That's going to be 0. Okay? So applying our initial conditions, ICs, we obtain something. Well, everything's going to be 0 except this. I'm going to get a minus s squared here. And I've still got that term over there, of course, and that term there. So we'll get something like this. Okay? So you can see that's simplified now. Now, I'm at the algebraic stage. What I want to do is solve that algebraic expression for big Y of S. Okay, so let's just say bring that s squared to the other side, factorise the big Y of S, and then simplify. So if I rearrange, I get this. So this now is a solution to our transformed state. Okay? Now, if this is the transform of little y of t, how would I get little y of t out of this? Take the inverse transform. Okay? So if I can calculate the inverse transform of s squared on s to the 4 minus 1, I actually get the solution to my original problem. Okay? So we're at a milestone here. We have solved for the transform of the function that satisfies these conditions. What we're going to do is sort of take the inverse transform. Okay. Once we can do that, we actually have the solution to our original problem, which is great. Now, sometimes the inverse transform is easy and sometimes it's not so easy. Now, you sort of, some students, because they look at this and they're conditioned to use partial fractions. All right? If you look down the table, we want something like a s squared on s to the 4 minus 1. Well, there's nothing, if you look up here, there's nothing exactly like that. Okay? So what is common is to split that s squared on s to the power 4 minus 1 up into partial fractions, right? Using partial fractions. Is it needed in this case? No. By adding and taking something away, you can actually simplify this without using partial fractions. Okay, so let me show you what I mean. This isn't always possible, but in my experience, it's possible quite often. Okay, so let me show you. Now, the first thing we know, that the bottom bit will factorise, right, into something like s squared minus 1, s squared plus 1. Note I've got an s squared up the top. What I can do is say add 1 to the top and take 1 away and see if I can get some nice cancellation when I expand it. So let me show you what I mean. Okay, so I've done the factorisation. And if I look at the s squared, well, it's almost like s squared plus 1 and it's almost like s squared minus 1. So let's just try to get it like 1 or both of those. Okay, so I've put it in the following form. All right, well, if I sort of bracket it this way, and I sort of just write it as the sum of two things, I can get the following. The s squareds plus 1 are going to cancel in the first term. So I'm going to have that. And then in the second term, well, I'm kind of stuck with this. Okay? So you might think, well, hang on, have I actually simplified things there? Well, I can take the inverse transform of that. That's in the table. So it's all about this now. What can I do with this? Well, why don't I just have another go? Maybe I can add s squared in there and take s squared away. That'll give me an s squared plus 1, and I see an s squared plus 1 down there. Maybe that'll simplify. So if I bracket it like that, I come up with the following. Again, just writing this out as two parts. So I should get something like this. Sorry. Yep. And then I'll get something like this. Now this minus s squared is going to be on all of that. Now if you look closely, I'm going to get the same thing over here, but with a minus sign. So don't worry about those brackets anymore. Okay, so can anyone think how we can simplify? If I just take that to the other side, I get 2 lots s squared over that. So then I can just divide by both sides by 2. Okay, take that to the other side and then divide both sides by 2. Hang on, I think I'm missing a minus sign here. No, that's okay. Good. Now you may look at that and go, well, I don't like that. Well, if you want to use partial fractions, be my guest. Okay, that method won't always work, but what I'm trying to teach you is to, like, you know, sort of just playing with the numerator sometimes can greatly simplify steps. And in my experience, students sort of get conditioned into using partial fractions, right? When actually it's not necessary for a lot of problems. Okay, now the point is I can calculate the inverse of that from a table and that from a table. So let's do it. So our solution is the inverse transform, which is just the inverse transform of this. Again, it's the inverse transform. So I just need to look these two things up in the table. Okay, well, let's have a look. The inverse transform of 1 on s squared plus 1. It's going to be something like sine 1t. So that'll give me sine t there. And the inverse transform of 1 on s squared minus 1. Okay, so it's going to be something like that one there, sine bt with b equals 1. You know, going from that step to that step is the key. Okay, so the question is, how did I come up with those things? Well, it's from these forms down here. You want to add something that simplifies and at least and crosses off with at least one of those factors in the denominator.